All right, so this is my second examples. Okay, so this is minus, just make sure, and this is minus, not plus. And again, this is a system of ODEs, and we can write down as into the system of ODE with such kind of matrix form. And basically, again, we are trying to solve as x prime equal to a times x. Okay? And we're using ansatz, again, this, and basically we transform this into eigenvalue problems. For now, I suggest you pause the video and just do it at to solve the eigenvalues and eigenvectors, see whether it matches to the solutions or not. All right, hopefully you just find out the eigenvalues and eigenvectors. And let me just tell you the solutions. The eigenvalue, there are two eigenvalues. First one is -4. And the corresponding eigenvector, it's 1 minus square root of 2 divided by 2. And this is equal to -1. And the V2 is equal to 1 and the square root of 2. Okay? And you can see for these two lambdas, and they are less than zeros. Okay? So we can write down the solution, and it looks something like that. Of exponential of -4t plus c2 of exponential of -t. Right? So if I ask you what is the long-time behavior for this solution, and probably it's very clear because this decays to 0 and this decays to 0, and this what goes to 0. But we want to show that in the phase plane diagrams. So again, I'm going to plot by hand and show it. And after that, I will just repeat the same thing in the PP plane and show that correctly. Okay, hopefully this is good enough. Again, this is x1 and x2. So the techniques is exactly the same. We trying to find out some cases such that C1 equal to 1 and C2 equal to 0. And such that this our solution, which is x1, x2, looks like exponential of -4t minus this times exponential of -4t. All right? So again, we can write down as linear lines. As you can see, it's always we can write down the linear lines. But turns out this is not always true, and we will give you more examples later on, probably when I come back. The solution looks like this. Again. But this time, as t goes to infinities, they will go to 0. So the arrows is, coming down to the zeros. Right? And because as t goes to infinities, this one goes to 0, 0. Number 2, C1 equal to 0. Find out some initial condition, make this is true. And this is C1, x1, x2 again becomes exponential of -t square root 2 exponential of -t. Okay? So we can using the straight line again to express it out, which x1 times square root 2 equal to x2. All right, so again, we can just write on this straight line. pretty much easily. But this time, again, as t goes to infinities, it goes to 0. So for all these two lines, and they always goes to 0. I mean, obviously, for the solution in the middle, they always, and they should also goes to 0 as well. But as you can see, for this solution, they goes 0 faster than this one, right? So, I mean, because the number here is -4, and the 4 is larger than 1. So basically, what we left is, so this term is like decays to 0 very fast, and this term will be dominated right here. So later on, I think maybe will be dominated. Maybe it's like something like this, more dominated by this direction. Hopefully this is right. So all arrows will goes to zeros. No matter where they start, no matter where they end. And no matter where they start, they always goes to zeros. And you can see this is basically like flower, and everything and every arrows will point to 0, 0. So this is called a stable fixed point. Okay, and sometimes we also call it sink. Right. So obviously this is like sink, and it goes to 0. So it looks like something like sink. Okay, so more precisely, it's called a sink node. Okay. So sink is because lambda 1 is less than 0 and the lambda 2 is less than 0. For the node is because lambda 1 and the lambda 2 are real and distinct. So obviously, our previous example for the saddle point, and they are also a node, but they are not sink. And because the requirement for the sink is both eigenvalues are less than 0. But the saddle point is 1 is larger than 0 and 1 is less than 0. But for this case, it is stable. And the reason, as you can see, they always goes to 0. And if I just perturb my solution around 0, it will, bouncing back to 0 anyway. So let's verify this in the PP plane. Hopefully, I can get it. So the way that we can write on is -3 plus squared, which represent by SQRT of 2 times x times y. SQRT 2 times x minus 2 times y. Proceed. Okay, this is the graph that you will see. If we just say this is our initial condition, and you can see every solution goes to 0, will point to zeros. All right, so let's just plot a few more. Okay, as you can see, and we have 2 lines and 2 straight line. One is something like that, and the one is something like that, and this is coincident, and the corresponding one here and the one over there. But all the graph is, and it will point to zeros. It's very clear.